Welcome back. I wish I could see you. I can imagine you there. I can see some of you in my mind's eye. I wish I knew all your names. I miss you. Okay, we're going to do a little bit of relativity review. Let's look at an iron 56 nucleus. Iron 56 nucleus, as are all nuclei above hydrogen. The nuclei are mixtures of protons and neutrons. An iron 56 has 26 protons and 30 neutrons in the nucleus. The masses of the protons and the neutrons are well known. Common unit to use is the atomic mass unit, which is 1.66 times 10 to the minus 27 kilograms. And in those units, the proton is 1.0073 AMU, or atomic mass units, and the neutron is 1.0087 AMU. If you add those all up, you get 56.45 AMU. That should be the mass of the iron 56 nucleus. But we can measure that too, and it's 55.94. A half a neutron is missing from the iron 56 nucleus. It doesn't add up. And the reason it doesn't add up is because the energy of the iron 56 nucleus, in addition to having the rest energies of all the particles that make it up, there's some negative potential energy. The neutrons and the protons are bound to each other. They're down in a deep negative potential energy well, so deep that the energy equivalent of that well is a half a neutron, mc squared. This is a binding energy of 475 mega million electron volts. Just to compare, an electron is bound to a hydrogen atom by about 13.6 eV, 36 million times less binding energy. That 13 eV amount of energy is enough to make all of chemistry happen. So dynamite, forest fires, burning natural gas to heat your house, that all comes from chemical mass loss with energies on the order of a few electron volts. If you make a reaction happen with a nucleus with hundreds of millions of electron volts available, well, there's a lot more energy available there. A really good example of that is the sun. The sun is on fire, but it's nuclear fire, and it puts out a lot more energy than if it were just a chemical fire. Okay, let's review something that was in the book that I didn't talk about last time. This is energy and momentum in relativity. Sometimes it's more useful to use these relations I'm going to show you than to tediously go through gamma, find the velocity, get gamma, use all the formulas that have gamma in them. There are relations between energy and momentum that don't go through the velocity. That's true in Newton's theory as well. The energy is 1/2 mv squared, which can be written as p squared over 2m, and you can just forget about the velocity. Solving that for p, you get p is equal to the square root of 2me. These relations are wrong in relativity, but there are relations still that work. The energy is related to the momentum by the one on the left. The energy is the square root of m squared c to the fourth. That's the square of the rest energy, plus p squared c squared, where p is the momentum. If you solve that for p, you get p is the square root of e squared over c squared minus m squared c squared. This can be very useful for homework problems where you know energy and momentum, and you just as soon not mess with gamma and velocity and all of that stuff. So I recommend those formulas to you. Okay, here are some questions from last time. The Doppler shift formula for light from a star coming directly at us is what? Which one of these? And so we're looking for one that shifts up and has the proper relativistic formula, and it is A, as many of you knew. The formula for momentum in relativity is which of these? That one's B. The formula for rest energy, the energy of something that's not moving. The rest energy formula is very famous, E equals mc squared. And then when you allow it to move, the total energy becomes gamma mc squared, which is B, but B is not correct because that's not the kinetic energy. The kinetic energy is the total energy minus the rest energy, and so that one is C. All right. As I mentioned before, I have good news and bad news. I'm going to sound deranged now for the rest of the semester. That's the bad news. The good news is that I can't give you any real problems. And so the problems aren't going to be so hard. Mostly, you'll just have to understand qualitatively how everything fits together and then put numbers into formulas from the book or from the chapter summaries. And that will be true until we get to nuclear, and then you'll have some real problems again. But for the next little while, it's just going to be plug and chug, I think is what we used to call that. So, in chapter 6, we begin quantum mechanics. With relativity, it's our current best shot at how the universe works. You may be surprised to see that I'm wearing Albert Einstein again, and that's for an amazing reason. In 1905, when Albert Einstein published his paper on the theory of relativity, which we've discussed for the last 3 times, he also published a paper that helped put the nail in the coffin of all the people who didn't believe in atoms anymore, and he used Brownian motion, an analysis of Brownian motion, to make an estimate of Avogadro's number, which is a number you need to know if you're going to believe in atoms. And in that same year, he basically invented quantum mechanics. I don't think there's ever been a year when a scientist published 3 papers that were as important as those papers that Albert Einstein published in 1905. You've read about this, so I can quiz you on it a little bit. Light is a what? A wave, a particle, or some weird thing that's both? And the answer is it's some weird thing that's both, and that's what we're going to talk about today. Planck's constant, which shows up in quantum mechanics prominently. It's always good in physics to ask what the units of something are. Planck's constant has units of, and there's a very good chance you don't know this, but you should memorize this. It's very helpful. Planck's constant has units of angular momentum, which also turns out to be the same as the units of energy times time. And both of those turn out to be important ways of thinking about Planck's constant. Okay, at the end of the 1800s, some scientists thought that our understanding of the physical world was pretty much complete. There were just a couple of things that needed to be cleared up, and then physicists wouldn't have anything to do anymore. Today we'll discuss a few of these last-minute details, experiments that didn't quite make sense and that needed to be interpreted in terms of Newton's laws and Maxwell's electromagnetism, but they didn't get cleared up. They just wrecked everything and they made us start over. The first was the problem of catching a light wave, which, as the young Albert Einstein realized, made no sense. If you caught a light wave so that the electric and magnetic fields were just stationary, then they couldn't change in time and make each other, which made no sense. That led to relativity. The second set of details, which we'll discuss today, led to quantum mechanics. And out of this wreckage came all of these things that you're used to in the modern technological world that we live in. So in about 1900, we had 2 separate physical models for how things behaved. If you had something that was a mass that was moving, like a bullet or a car or an airplane or a ship, you analyze that by focusing on the mass of this object and what forces acted on it and how it accelerated. And you can predict all kinds of things in the world we live in just by using that. But then there are things that don't work that way. Things that are waves, things like light and sound, earthquake, vibrations that propagate through the Earth's surface, like the one that shook my bed up and down at about 3 hertz and an amplitude of about 3 centimeters about a week ago. There's all that wave stuff, and you have to worry about phase, and there's interference, and you can make images. And that's a separate subject. Well, in quantum mechanics, it turned out for in certain situations, mostly having to do with very small particles, atoms, electrons, protons, and neutrons. The bullets behave like waves, and the wave phenomena on that scale behave like bullets. And you can't decide which one it is. They behave as if they were both simultaneously. And that's almost impossible to think about, but the mathematics that goes with it is perfectly clear, and you can calculate exactly what's going to happen in experiments without understanding in the picture sense of things what's happening. So remember the two-slit interference pattern. You have light coming in to a screen that has two slits in it, and on the other side of that screen there's an interference pattern. If you do this experiment with very dim light, so dim that only one photon, you read about photons, so that only one photon at a time is incident on the screen, it doesn't wreck the pattern. The pattern is still there. The way the pattern happens is that no photons that come through the slits ever go to the dark spots. They go to the light spots where they're detected as one dot on the screen. And then if you do this a billion times, the pattern gradually builds up. And this is happening with one photon incident on the slits. That's completely crazy. And there are a lot of other things that are crazy too. And I'm now going to go through 4 of them. This will seem kind of long. I'm going to go through 4 of them and try to convince you that this idea that energy comes in discrete packets, as Max Planck and Albert Einstein proposed, and that the amount of energy they have is proportional to this constant called Planck's constant. I'm going to try to convince you that it actually makes sense and explain some important things that we didn't understand before. Let's begin with degrees of freedom, which you remember from our discussing ideal gases. And you can read about this in the chapter summaries. I think the discussion there is better, or maybe the only one you're going to get out, because I don't think the book has this. Okay, so when we discussed degrees of freedom, we learned that in a monatomic ideal gas, the average value of 1/2 mv squared, which is the average value of the energy that the molecules have, is 3/2 kT. And in general, the average internal energy stored in an ideal gas is the number of degrees of freedom divided by 2 times kT. And then we learned that for diatomic molecules, the number of degrees of freedom was 5, even though there are 3 axes that diatomic molecule could rotate around. It's like one of them is missing. I'm going to explain to you now why that's missing. And here's the reason. In quantum mechanics, things that we thought could have any possible value turn out to be quantized, meaning that they come in discrete bits. And one of these things that's quantized is angular momentum. It means that when a ballet dancer spins around her pointed toe, she has angular momentum. Her angular momentum must be an integer multiple of Planck's constant. Now, this is not hard to do because Planck's constant is so small, 10 to the minus 34 small. She can switch from having 65 gazillion trillion to 66 gazillion trillion without a blink of an eye. It's easy to change her angular momentum. But for very small objects like atoms, and in particular like diatomic atoms, those atoms, molecules, can't spin at just any frequency they want. They can not spin, which is okay, having 0 angular momentum, but the first frequency they can spin at above 0 is the frequency h bar. This frequency is the angular momentum of the first one up is h bar, which has units of angular momentum, and that's one of the things it means. It means that angular momentum can be 0, or h bar, or 2h bar, or 3h bar. It can't be 2.5. It can't be 3.1. The angular momentum of something that spins on the atomic level Has to be a multiple of h bar. So let's go see what that means for one of these atoms. The energy that a spinning object has, you might remember from Physics 121, is 1/2 times the moment of inertia times omega squared. This is the spinning equivalent formula of 1/2 mv squared for translational velocity. It's 1/2 moment of inertia omega squared. You can convert that into an angular momentum formula by using that the angular momentum is an integer multiple of h bar, nh bar, and solve for L, or solve for, it's also equal to I omega. That should be on the slide. I'll fix that. The angular momentum is nh bar, and it's also I omega. And so you can solve for omega in terms of L, and it looks like this: 1/2 L squared over the moment of inertia. Well, that means that if the moment of inertia is incredibly small, that the first spinning level that you can get to would have a very big energy, and the molecules around your the air molecules for these little dumbbells, there might not be enough energy in the average kinetic energy of the molecules as they move around to bump it up to spinning about that axis where I is very small. So there are 3 axes that you could have the diatomic ideal gas spin around. You have to remember the moment of inertia is mass times radius squared. There are 2 axes that go through the center of mass of this nitrogen molecule, up and down and sideways, right through the center of mass. And for those 2 axes, the nuclei are quite far apart, quite far away from the axis of rotation, and they have reasonable moments of inertia for being as small as it is. But if you take the 3rd axis, which has to go through each nucleus, so imagine putting a rod from left to right diagonally through this molecule so that that axis goes through both nuclei, the nucleus is 100,000 times smaller than the atom itself. The radius in the I equals mr squared formula is so incredibly small already, and then when you square it, it's ridiculously small. That makes the moment of inertia be tiny. And so what happens, if you actually look at the details of, say, nitrogen, the sideways moment of inertia is 6 times 10 to the minus 46, and the long way, it's about 10 to the minus 56. 10 billion times smaller. And because that nucleus is so small, to get that thing to spin with 1 quantum of Planck angular momentum, 1 h bar of angular momentum, would require an energy of 4 times 10 to the minus 21 joules. But the molecules in the gas, well, 10 to the minus 13 joules, sorry. The molecules in the gas just don't have that much energy. So as the molecule gets bumped, it naturally gets kicked and spins around 2 of its axes, but that 3rd one that goes through the nucleus, it never spins around that one until the gas gets incredibly hot, like as hot as the center of the sun. Okay, so one of those rotational degrees of freedom can't participate in storing energy, and that changes the formula for the internal energy. There are a whole bunch more that can't participate either. Each of the vibration modes of this dumbbell molecule, you can imagine the 2 nuclei getting closer and further apart. There are a bunch of vibrational degrees of freedom too, and they have energies that are way too high for bumping into other molecules to excite, and so those aren't there. And so there are only 5 of them that can participate at room temperature, 3 translational and 2 rotational, and that's why a diatomic gas has 5 degrees of freedom. Okay, here's another way that this quantum idea becomes important, and this in fact was the beginning of the whole thing. If you take a black object, a black hollow object, punch a small hole in the side of it and then get it really hot, maybe with a blowtorch or something. As it gets hot, the metal will, you've seen metal get hot, it glows red hot, then it goes white hot. If you put a spectrum analyzer up to that tiny hole and look at the spectrum of the light that comes out of it, it looks like this. It looks a lot like the velocity distribution of speeds in an ideal gas. There aren't any low frequency. There's not any for low frequency light. Then there's a place where it peaks. That's where the light is, probability of finding light at that frequency is maximum. And then instead of going up forever, it comes back down again. So there's a low probability of finding very high frequency light. To physicists in around 1900, this made no sense whatsoever, because the way they thought about these things was that each three-dimensional standing wave of light in a cavity is a degree of freedom. And up at the short wavelength end, you can have tons of standing waves. You could have 50 in vertical and 57 horizontal and 65 horizontal in the other direction. And there's just so many modes of vibration for the light. And each one of those should have 1/2 kT of energy in it. And so this curve, this one, the curve that goes up and then comes down, should just keep going up and up forever, but it doesn't happen. Something out here kills the high frequency tail, and it was a complete mystery. Nobody had any idea what was killing that off. Well, Max Planck worked on this. He worked on it for years, and he was mostly not trying to understand it. Finally, he tried to understand it and he couldn't. So then he thought, well, maybe if I just throw some physics ideas at it and invent crazy stuff, maybe I can find a formula that will at least fit it. I won't know why it's that way, but maybe I could fit a curve through the data. Well, he was more successful than even he imagined. The guesses that he made about how things worked was that the energies that you could have in the cavity, they weren't just any old thing you wanted. The energy stored in one of these modes was equal to a constant, which later became called Planck's constant. He didn't call it that to start with, times the frequency. And you can do this either with h bar, which is h over 2 pi, times the angular frequency, which is 2 pi times f, or you can use hf. And then he also added in the Boltzmann factor, which says that high energy states, like fast molecules, for instance, that they're unlikely if their energy is much higher than kT, the energy of the molecules around. This has the property that it can kill the high frequency mode energies, high frequency modes, because they have high energies. And so that's what happens with the distribution of speeds in a gas. That's on the left. That's what the distribution of speeds in a gas looks like. And there are no high-speed gas molecules because those molecules would have a ton of energy. And the probability that they would have that energy goes like e to the minus e over kT. So Planck put the same thing in to kill a high-frequency tail in the black body radiation spectrum. And if light were actually made of discrete bits of energy, then we could understand this. If light were made of little discrete packets of energy, there shouldn't be high energy ones. And that would mean there weren't high frequency ones either, if energy and frequency go together. Well, Planck's new formula, based on these two weird ideas, fitting them together, it fit the data perfectly if you chose the constant just right. The constant h was 6.626 times 10 to the minus 34 kilogram meters squared per second. And the light particle, Planck didn't actually think of light as being a particle with energy. He thought of the atoms somehow having their energies quantized into bits of his constant times frequency. But if you did that, you could fit the thing exactly. It was way too good to be an accident. He received the Nobel Prize for this, but he hated it. he wanted to figure out why you had to make this goofy assumption that the energy in this cavity came in quantized bits equal to his constant times their frequency. He wanted to figure out why that was true and have it make sense. He couldn't do it. He also didn't like the Boltzmann factor. He hated that too. Wasn't wild about the idea of atoms. But both of these things are observed in experiments now all the time. And he got the Nobel Prize in 1918 for inventing these ideas that he didn't believe in, but which worked. The person who took it seriously and said, no, this energy is equal to Planck's constant times frequency thing, that's not just the energy that atoms happen to be able to produce. Einstein said, this is what light is. Light is little packets of energy. Each one has an energy given by Planck's constant times its frequency. They come in little packets. We call them photons. So, for instance, when you turn a flashlight on, you are making little photon torpedoes that go across the room and light up whatever you're looking at. Einstein came to this conclusion for two reasons. Number one, he knew about Planck's photoelectric, Planck's blackbody spectrum idea, and he wondered what this HF thing really was. He also knew about the photoelectric effect, which is the property that if you shine light on certain kinds of metal, electrons will pop right out of the metal. It's mysterious, though. You'd think if you put high-intensity light shining into the metal, that it would make more electrons come out. But the intensity doesn't seem to matter at all unless the light is of high enough frequency. The photoelectric effect works way better if you use high-frequency light than low-frequency light. And in fact, the experimental data are very well described by this formula. It says that the maximum energy, the maximum kinetic energy that the electrons come out of the metal with is equal to Planck's constant times the frequency of the light that shines on the metal minus a number called the work function. This is how much energy you have to supply to an electron to get it to come out of the metal. Metals like to hold on to their electrons, and you have to give the electrons energy just to get them to come out at zero kinetic energy, and then if there's any extra left over, they can have some more kinetic energy. This is Einstein's formula, where he combined the energy ideas of Newton with Planck's idea of constant times frequency as an energy. And here's the story. This may not have made sense to you when you read it, so let me tell it to you again. This is the story of this Kmax equals HF minus phi. So, using Einstein's idea of photons, here comes a photon. The photon hits the metal, and the metal absorbs the photon's energy and then tries to figure out what to do with it. If the photon's energy is less than the amount by which the metal holds on to the electron, that energy is given to electrons, they bounce around inside the metal, and it just ends up being thermal internal energy in the metal. But as soon as the HF gets big enough that it exceeds this phi thing, this work function it's called, it's the potential energy that an electron is down in a well in the metal in. If the HF is bigger than that, then the electron can leave the building. The electron has enough energy now to climb out of the well that it's caught in, and then the leftover energy can make it come out and be detected as kinetic energy. It's called Kmax because it's the most that it can be. Something might happen to the electron on the way out. It might bump into atoms or other electrons and lose some of its energy before it came out, so that its kinetic energy when it got out would be less than Kmax. It might hit some air molecules after it leaves the metal. That would make its energy be less. But the most you could possibly have would be the energy that the photon gave it to start with, minus the potential energy that it had to climb out of the well, had to get to climb out of the well. And that's the story of this formula. These are Planck's constants. The first one, H, is used when you talk about frequency in hertz. H bar, which is Planck's constant divided by 2 pi, is the one you use when you want to get the energy by multiplying a constant times the angular frequency, and then you'd use H bar. So H bar goes with omega, and H goes to F. The metals that work with the photoelectric effect are the first vertical row in the periodic table. Their potential energy well, by which they hold on to electrons, is about 2 volts. And so electrons have to have 2 electron volts of energy or more to get out. And for these materials, beryllium and magnesium, calcium, strontium, barium, lithium and sodium are missing here. I'm not sure why. But anyway, those alkali metals over there, any color above red can pop electrons out of those metals. If you go in the middle, over in the transition metals, zinc is a popular one, for instance, just to the right of my arrow. It takes much higher frequency light to get electrons to come out of those metals. They have wells that are as deep as 4 electron volts. And so it takes ultraviolet light or higher frequency to get the electrons to pop out. And this is all observed in experiments. It's mysterious until you believe in the idea of photons and use Einstein's picture, which we just had on the previous slide. And everything works great. Okay, so here's what photons are. Photons are little packets, little packets of energy. Their energy is either h bar omega or hf. They both work. Relativity predicts that particles with zero mass should have an energy-momentum relation. This is this energy-momentum relation I showed you earlier. If you put the mass equal to 0 in there, it says the energy should be Pc. And if that's true, then the energy of the photon, hf, should be equal to Pc. So the momentum would be hf, the energy, divided by c. And then you have f over c. Well, that's just 1 over lambda. And so the momentum is predicted to be h over lambda. You can do experiments on that too, to see if photons behave as if they have momentum. And yes, they do. And the momentum of a photon is either h over lambda, or if you prefer using h bar, then you use k, which is 2 pi over lambda, and you let it be h bar k. They do have momentum. And you can do experiments to show that these formulas are exactly right. I mentioned this quantum mechanical energy unit. You don't really need to know where it comes from. It actually comes from the stuff you'll talk about in Physics 220. An electron volt is the energy that an electron would pick up if you accelerated it through a voltage difference of 1 volt. And that's why it's called an electron volt. But all you need to know is that 1 eV is 1.6 times 10 to the minus 19 joules. It's just an energy conversion, and it's much easier to talk about energies of these tiny sizes when we're talking about atoms. So red light, for instance, a red photon at 600 nanometers, its energy would be hc over lambda. If you work that out, it's 3.3 times 10 to the minus 19 joules, which is about 2 of these electron volts. Blue light, up at the other end of the spectrum, is at 3 eV. To get up to 4 eV, you have to go into the ultraviolet, as we saw on the previous slide with the photoelectric effect. I want you to go to YouTube and search for a video called The Photoelectric Effect Open Mind. Open Mind is the company that made it, or the organization that made it, or the 2 people in their living room with a camera that made it. Watch it. It's a nice little short animation. It'll give you a physical picture of how the photoelectric effect works. Okay, here's number 4. It's called Compton scattering. It was discovered in, I think in the 1920s about, that if X-rays were shot at the electrons in atoms, that the electrons could get knocked out of the atoms. Well, that's maybe not too surprising. The photons have energy, and they could give that energy to the electron and knock it out. But what was bizarre to some people was that there was also a photon that came out. The X-ray would come in, the electron would pop out, and another photon would also come out. But it was always of lower energy. And they had no detailed explanation of how this worked. Arthur Holly Compton, an American physicist at the time, did the following calculation. He said, look, if you're going to shoot X-rays, and if they're really photons, the way Einstein says, then you should be able to play like billiard balls. The energy has to be conserved. And so the HF, that's the HC over lambda naught, the HF naught, that's the original X-ray frequency energy coming in, would have to be equal to HC over the new wavelength, the scattered photon wavelength, plus gamma minus 1 times mass of electron c squared, because that would be the kinetic energy of the electron. So that's one equation. Another equation is that the momentum in the x direction would have to be conserved. That's the h over lambda naught equals h over lambda prime cosine theta formula. And the angular momentum in the y direction should also be conserved. And that's the equation at the bottom of the page. Professor Compton did some heroic algebra to turn that complicated calculation into a very simple formula that just predicts what the new wavelength, the scattered photon, would be in terms of the original photon wavelength, plus a constant that has Planck's constant in it, and the mass of the electron and the speed of light, and then the factor 1 minus cosine theta. This fit the experimental data perfectly. You'll notice, since this equation gives wavelengths, all of the terms in the equation must have units of length, including the h over MEC. That h over MEC turns out to be 0.002 nanometers. So you're not going to see this effect with red light at 600 nanometers or even blue light at 400 nanometers. This only matters for X-rays and gamma rays that have wavelengths short enough that they can compete with 0.002 nanometers, and that's exactly what's observed. I want you to go to YouTube and look for a video called Compton Scattering Animation, Binosa or Binosa, I don't know how to say it, but there's the spelling. If you type that into the search bar, you'll find it. I'd like you to watch that. It's only a minute or two, and that'll give you a physical picture of what's going on there. Okay, well, let's review by taking a quiz. Diatomic gases have 5 degrees of freedom because, I'll let you think about this. One of the 3 rotational degrees of freedom can't be energized at room temperature, and the rotational degree of freedom it is that can't be energized is rotation around the axis that goes through each nucleus in the diatomic molecule. The radii of the moments of inertia about that axis are so small because the nucleus is small that you get a very tiny moment of inertia, and you just can't energize that first quantum of angular momentum. It won't go. Planck and Einstein solved the black body radiation puzzle, spectrum puzzle, by guessing that. Which one of these? Yes, it's A. And the photoelectric effect shows, well, I messed that one up. It shows that light of high frequency can knock electrons out of a metal, while low frequency light can't. Now, what about that intensity thing? Suppose you have light of sufficiently high frequency that it can knock electrons out. What if you make that light be more intense? What happens then? Well, then you get more electrons. The more photons you have, the more electrons you'll get. That makes perfect sense. But if you have light of low frequency, too low, to knock an electron out. It doesn't matter how bright you make that light. No electrons will ever come out of the metal. In the Compton effect, light knocks electrons around as if light were a particle with energy and momentum. It's like playing billiards with photons and electrons, except that the billiard balls change color after they collide with an electron. Okay, you may be asking, this looks really hard. How am I supposed to do homework? Well, the homework is actually pretty easy. You just believe the formulas and put numbers in. When you're asked a question about degrees of freedom or black body spectrum or the photoelectric effect or Compton scattering, you find the formulas that apply to those and you put numbers in, and they'll probably be enough given that there's one thing that's unknown, and you use your algebra skills to solve for it. And I might mention, as you probably already figured out, that the chapter summaries are shorter for playing this game. And there's some more review questions, and I will see you next time.